Okay. So we are discussing completeness. And in the last class, I forgot one thing, one proposition, which I will prove now, and then we'll discuss more about Bayes' theorem, consequence of Bayes' theorem. So we will discuss one application today, and then we'll continue after midterm maybe. So this I forgot to, this is a property of norm-linear space. So to determine when a norm-linear space is complete, this criterion is very helpful. We can have more applications to this also. So let's be a normed linear space. NLS means normed linear space, maybe X with a norm. Okay. Let's be a normed linear space. Then X is complete if and only if every absolutely summable sequence or a series, whatever, summable sequence or any absolute, no, absolutely summable series, absolutely what is absolutely summable, what is okay, converging. I said sequence first, so they said summable, absolutely summable sequence. Absolutely converging what? Converging series converges. What it means is, if you have something, some sequence in X, such that summation norm Xn. This is what here you have norm here. Of course, modulus doesn't make sense, so infinity implies summation Xn, which is, of course, you take up to n equal to 1 to n or something. This converges. This limit exists. This converges. This converges to a limit. So proof, you can see that this is a bit powerful. For example, if you have functions, continuous functions, okay? So if you want to say that, if you say that that is absolutely summable as continuous functions on a compact set or C01 or something, then you can take the sum of that. For example, if you have summation fnx for something, it is, how do you, for each x, you may be knowing that it exists. But then how do you know this is a continuous function? Suppose if you show that it is absolutely summable, then that will converge uniformly, so that will be a continuous function. What is the statement? Every absolutely converging series converges. This is what it means. What is the problem? Summation xn, norm xn less than infinity. But this implies this. Whenever this happens, this should happen. This is the meaning of this. Right? What's the problem? If it is complete, then this happens. If this happens, if this happens for every sequence, every series, then it is complete. Okay? So we prove this way. Suppose X is complete. We assume X is complete. Okay? So then you want to prove that every absolutely converging series actually converges. Okay? So Xn be any series. So let Xn be such that summation norm Xn is less than infinity. You have to show that it converges. Okay? To show something converges, you have to show, since it is complete, so enough to show, enough to prove this sequence, this is quotient, right? In N is quotient. Okay? If you wish this as a sequence, Yn is.
Then like the other side, non the other direction should be the non-general.
Of course, yeah.
This.
we can prove trivial direction and come to a non-trivial direction. No problem. So, since X is complete, you have to prove this is Cauchy. Okay. This is, I mean, this you call it as yn or something. That sequence is Cauchy. That's what we have to prove. This series converges means that sequence is Cauchy. So this is Cauchy means you have to prove that xn minus xm, yn minus some ym goes to 0 for as n and m goes to 0. That is, we need to prove summation n equal to n. I mean, sorry, n equal to k equal to n to m xm. It goes to 0. This is what you have to prove. To prove something goes to 0, it is enough to prove norm goes to 0. Okay. So, but summation k equal to n to m, norm of this xn is of course triangle inequality less than or equal to k equal to n to m, norm x, norm xk, sorry, xk. This of course goes to 0 because of absolute, because that's what it means by absolutely summable. This is exactly equal to 0. So this is clear. Where this is, that is. Okay.
Wait. What?
You want this goes to 0. Norm goes to 0. This is less than or equal to this. This goes to 0 because you are assuming absolute convergence. In this true, Mithla? Is it? It is true. Okay, think about it. And it's okay to everyone.
This is true for n is equal to 1 and m is equal to infinity also.
Yeah, that's what it means by converging, something converging.
So, value
of
the series,
yeah,
infinite series exists.
Exactly, less than infinity.
But that doesn't imply the series exists.
That is true, you know, for real line. This is true. This says it's true for because real line is complete. Okay,
so
that's the question. In general, it's not true in a non-linear space. That is not true. Okay, for example, you take a vector space, rationals. Rationals are not a vector space over R, but I mean, you take rationals over rationals if you want. Okay, then that is not true. Okay, in general, in a incomplete non-linear space, this is not true. You know this as a result in real line. Okay, that is your confusion. That is because R is complete. Okay.
Where are we using the complete?
It's enough to prove it's Cauchy. That is completeness. Okay.
The Q is not complete. That would mean the series Q.
Yeah.
Like some bonds is.
That can go to, yeah, that can go to some real line. So it's not. What is the example of that? Yeah. Q over Q, for example. No, if you want, I'm just saying, I just gave an example. Non-example, there are plenty. Okay, you can take just all finite sequence with finitely many elements that can converge to something. Okay, you can use. There are examples, many examples in incomplete. For example, well, I mean, it's possible. Okay, yeah. So, okay, this is for complete spaces. So now we want to prove that if every absolutely converging series converges, then we want to prove it's complete. Okay, we want to use the second criterion to prove it's complete. Okay, so we want to prove this. So we let us take, suppose, some xn. We want to prove it's complete. So suppose some xn is Cauchy. We want to prove it has a limit. That's what we want to prove, right? That's what completeness means. Okay. We take a Cauchy sequence. We want to get a limit for it. Okay. So since it is Cauchy, there exists n1 such that since xn Cauchy, there exists n1 such that norm xn minus xn1 is less than 1, okay, if n is greater than or equal to n1. So like this, you do it for 2 and other things. So there exists nk such that xn minus xnk is less than 1 by 2 power k for all n greater than or equal to nk. Okay, because it's Cauchy, you can do this. Okay, this is the definition. I'm just using the definition of Cauchy. So these things in particular implies for this subsequence, subsequence x n k, k equal to 1 to infinity, x n k plus 1 minus x n k is less than 1 by 2 power k. I mean, that is true for all n greater than that. In particular, for k plus 1, that is true. Okay, I'm just using k plus 1, this is true. Okay. I mean, I have taken, for a reason, I have taken 1 by 2 power k, which is summable. So this implies summation n equal to 1 to infinity norm xn k plus 1 minus, this is the telescoping series idea. This is less than or equal to infinity, which is just the sum of 1 by 2 power k, which is less than or equal to infinity. This implies this. Just sum it. This sum is 1. So this is true. Okay. So this implies, so from our assumption, by our assumption that every absolutely converging sequence is converging, is a series is converging, by our assumption, summation k equal to 1 to infinity xk plus 1 minus xk converges. That has a limit. Okay. Say converges to, say, some x in x. Okay. It converges to some x. Okay. So, but then this is huh? Yeah. Won't it be? What? Say it again. Ah, right. Yeah. So I wanted to call it, yeah, nk. Yeah, correct. This converges. But this is just x1 plus x n, x n n, okay? Converges to x. Okay. This in particular implies xn has a convergent subsequence. I mean, you can take that x1 that side and this will converge. xn as a convergent subsequence. Okay. Hmm? You just sum it, no? It will cancel. Ah. Hmm? xn, no, nk plus 1 maybe, doesn't matter.
It doesn't matter. I'm saying if that should be minus.
Which should be minus? X1 minus x1, okay. Yeah, okay. This converges to x1. Okay. Okay. This is okay? Yeah, subscript doesn't.
N plus
No, no, k, nk, n plus 1. This is k, n plus 1. I think n plus 1.
Oh, N1. It will be N1. Okay.
Which one n1? Ah, okay.
N1.
Correct. Correct. Yeah, that should be n1. Right. The first term. Only the first term and nth term remains. The point is, this has a convergent subsequence. That is the convergence, that x and k is a convergent subsequence. So this has a convergent subsequence. So a Cauchy sequence, if it has a convergent subsequence, you know that it has a limit. Okay? Since xn is already Cauchy, assumed to be Cauchy, xn converges. Okay? That's all. That's what we wanted to prove. It's complete. Okay? So it's complete. For example, if you take a series of functions, okay, how do you know you may know that limit exists for each x. Using real line technique, you can prove that. But how do you know the limit is continuous? Limit is continuous if it is, so just think about it. Okay. If you show absolute convergence in this way, you can show the limit is continuous. Think about why it is true. Okay. I mean, how to apply that. I don't want to give the example. Okay. Think about it. Xn is a sequence. No. Cauchy sequence having a convergence subsequence is converges. Eh? You assume Cauchy sequence that converges. That means it's complete. What else completeness is? Completeness is that. You assume the second criterion. Every absolute convergence sequence converges as a series. Then any Cauchy sequence will have a limit. That's what it says. That's all. Well, even while defining quotient space and other things, this has application. But we are not discussing non-linear spaces here. So it's just an application. So it has application in functional analysis, but we are not doing that. Okay. Okay. Then we proved Bayes' theorem in the last class. Bayes' theorem says that if X is complete, X is any metric space, is complete, then X is of second category. Second category. That means X cannot be written as, that is, X cannot be written, I mean, I have to write that, cannot be written as union of Fn with, it cannot be written as countable union of nowhere dense subset. Whenever I say nowhere dense, it's only for closed set, okay? Because so this is closed and nowhere dense. This, I mean, union of n equal to 1 with Fn nowhere dense. If X is complete, Bayes' theorem says that if X is complete, then it cannot be written as countable union of nowhere dense subset. Okay. So, as a proposition, again, X is a normed linear space. Okay. Then X cannot be, X is not union of, maybe cannot be written is okay, not a, then X is not a union of, it cannot be written as union of proper closed subspaces. That is, if you have, I mean, maybe increasing or something, but if you have some space, then you cannot have some Kn such that union of Kn, maybe it's increasing, okay, is equal to X. For an example, if you take L2, okay, then you take sequences up to n, okay, that is all those. So let xn equal to all those x1 up to xn, then 0, 0 everywhere. Okay, you take this kind of spaces. This is the proper subspace. But if you take union of xn, okay, that will not be equal to L2. You need to take the closure. Okay. This cannot be written as like that. Okay. This is just the set union. You are not taking the closure yet. So any non-linear space sorry. Good. It's complete. Otherwise, there is no point in writing a complete non-linear space. Of course, whatever I said, I mean, you can just take the union of that. That is anyway a non-linear space. There is no point in that. So it should be complete, of course. Okay. Otherwise, there is no. You can always take union, increasing union. If it is increasing union, it will be a vector space, and the norm will be there. So this is not true for in general. Should be a complete non-linear space. So all we have to show that any proper, I mean, it's not written as, sorry, I mean, whenever I say, I forgot to say that, countable union. Otherwise, there is no point. In uncountable union, anything you can say. Sorry, uncountable union, anybody can say. Countable union, I'm sorry. I mean, this is deal with Baer's theorem, so you have to take countable union and all that. Okay? So any complete non-linear space cannot be written as countable union of proper closed subspace. All we need to prove by Baer's theorem, all we need to prove is any proper subspace is nowhere dense. That's what we have to prove. That's very easy. Okay, you only need to prove. You only need to prove if K contained in X's and it's not equal to this. Of course, if it is zero space, then it is of course nowhere dense. We don't have to worry. If not equal to X, okay, is closed. Okay. Then, I mean, we talk about nowhere dense only for closes. Otherwise, you have to take the closure. Okay. Then K is nowhere dense. That's what we have to prove. And the proof is very simple. So K is not equal to X. Okay. K is not everything. So there exists Y not in K. Okay. Here, there is no union. There is union. Closed proper subspace. You only have to prove it's nowhere dense. Then Baer's theorem says that. Okay. Thanks to Baer's theorem. Thanks to Baer. Okay. This is what we need to prove. We only need to prove this. Okay. So since K is not everything, there exists a Y which is such that, I mean, when I say norm Y equal to 1. Since K is not equal to everything, then there exists a Y, and Y divided by norm Y will be of norm 1, right? So you can take that. If Y is there, Y divided by norm is also not there. Otherwise, it will imply, I mean, exactly. Okay. So, and let X is in K. Okay. Then X plus epsilon times Y is not in K, right? For all epsilon. If X plus epsilon Y is in K, okay, then X is in K, then because it's a vector space, epsilon Y will be here. Y will be there. It's not the case. Okay. So X plus epsilon Y is not there. That's clear, right? X is in K, Y is not in K. So X plus epsilon Y is not in K. Okay, because it's a vector space. Okay? So this is not there. Now, norm X minus X plus epsilon Y equal to just epsilon Y, whose norm is just epsilon. Just direct calculation. So this implies B of X epsilon intersection K complement is not equal to empty for all epsilon. Okay. That's what this means, right? You take open ball around this, there is something, some element in there. Intersection K complement is not empty for all epsilon. That's what every open ball, there is no open ball completely contained in that. Every open ball intersects the complement. That means it is nowhere dense. Okay. Huh? There is no real vector space. Why? Complex you can take. Epsilon is a complex number also. Complex, huh? What? No, epsilon greater than 0 I am taking. This is the radius of this. Why norm epsilon? What's the problem? I am taking an epsilon and do this. I am taking epsilon. I can multiply with epsilon. Epsilon is also a complex number. If you want, real numbers are complex number. Okay. Because nowhere dense, I always assume the set to be closed to prove something nowhere dense. Otherwise, I have to take the closure. Okay. This implies K is nowhere dense. Okay. That which step? Here to here. Here. This is the definition of nowhere dense. Nowhere dense means what? Interior is empty. Interior is empty. There is no open ball completely contained in there. So you take any open ball that's going to intersect with the complement. That means it's that. Huh?
Complex.
He objected that it's a complex vector space. I said epsilon real means it's also a complex number. That's a joke. Huh? Huh? I am just saying he was objecting it's a complex vector space. So I said epsilon is also a complex number. I said I take epsilon greater than 0. That's also a complex number. If you are worried about it, I am just taking some epsilon greater than 0. It's not epsilon is given to me. Okay, so that is done. So the rest of the class I will prove that in C01 nowhere differentiable functions are of second category. It's dense, of course, second category. Of course, differentiable functions are dense. You take C01, okay? Then we have defined C01, C101, all continuously differentiable functions. This is contained in C01, is dense because polynomial itself are dense there. Polynomial itself are dense, so they are differentiable. So all continuously differentiable functions are dense there, okay? But then nowhere differentiable functions are also dense there. But what's the difference? Rational numbers are dense in real numbers. Irrational numbers are dense in real numbers. But we know irrational numbers are much larger than rational numbers. What it means? Both are infinite. What it means? Irrational numbers are countable, irrational numbers are uncountable. So the cardinality means number of elements, but here the number of elements is infinite. There are different kinds of infinity: countable infinity, uncountable infinity. Okay, what's the joke? Okay, so uncountable infinity is a different cardinality. It is like the power set of countable thing. Okay, so rational numbers are much larger in number. Okay, here it's not about cardinality. Here it's a topological statement. It's a topological statement. Okay, this is dense in C01. Okay, and we will show that nowhere dense, not nowhere dense, nowhere differentiable functions are also dense there. Differentiable functions are dense there. Nowhere differentiable, not even a single point. You cannot draw it any point, and still it is continuous. It is continuous, but it's not differentiable everywhere. Everywhere there's a peak. How will you draw that? Okay, to construct one such function, it took a long time. I mean, earlier, 100 years back. Yeah. So that is in 18, I mean, much before, okay, when people were studying basic function theory. But then now we can prove that such function, there's not just one function. Usually in mathematics, whenever some construction is very difficult and you could actually prove there exists one thing and it is something exotic, like it's very complicated or something, you would expect that to be in very large number. Then I mean, it should be uncountable. If this is usual natural things are like rational numbers, which are countable, irrational numbers which we can't handle, that will be uncountable. That is how it will be like that. Okay, whenever you have any kind of objects, I mean, it's a pattern. I'm saying it's not a theorem or something. It's not a meta theorem or something. And you cannot assume. That's how it happens in anything. Okay, whenever in any, I mean, I don't want to. I cannot give all such examples. There are many examples wherever the category or whatever, many objects. Okay, many objects in mathematics which you think are exotic, like it's not usual, it doesn't behave usual, but you expect it to behave like that. If it doesn't behave naturally, whatever you consider as natural, then they will be huge in number, much whatever it means, much bigger than the usual objects. Okay, so whatever you usually when you say a continuous function, it will look like this. That means it is differentiable. Okay, or at least it can be something like this. Maybe there are some peaks. Okay, it will be differentiable almost everywhere. That's what you will think. But there are continuous functions which are of second category. Okay, so this is the theorem we want to prove. Nowhere, let me just change. Nowhere dense, nowhere differentiable continuous functions forms second category. Is of second category. Okay, I mean, it is in C01. Or we say that functions, if d equal to f from C01, okay, to, sorry, f from 01 to real line, C or real line, doesn't matter. Let's take real line, okay, real line, such that f is differentiable at some, for some, at some x0 in 01. Okay, you call this D. Then this is a first category. Okay. If a subset is first category and the whole space is second category, then the complement should be second category. If not, you take this as countable union of over-density, this as countable union of over-density, take the both the unions, that will be okay. So complement has to be second category. Okay, that is, again, this means D equal to union of Fn. D is contained in union, maybe contained in union of Fn, with Fn closed, of course, and no valence. I mean, we have to show it's closed, so closed and no valence. That's what it means by it's equal, but it's contained in that is fine. You can take the intersection if you want. Fn is no valence. Each Fn is no valence. And at least one, maybe more. At least one, or some. Some means at least one. There exists a point where it is differentiable. Maybe it's not differentiable everywhere else. Okay, that's what we want to prove. So proof. So D, which is all functions differentiable at one point, okay, is contained in, let's write En, okay, equal to all function from 01 to R, or let's say f in C01, such that
There are that category one.
to this
Here,
here to here, and this is the meaning of this.
the definition was equal to.
You can take intersection and take the closure. I mean,
a subset of a first category set is first category.
That is true. Yeah, that's also true. You cannot have a second category inside a first category. Okay, those things are clear. So I want to say that D is contained in some n equal to infinity Fn. It's enough to prove that. I'm not saying it is equal, because this may not be close. So I mean, it's enough. I mean, it's equal, but it's okay. I mean, this is what we will prove. Okay? Maybe I will erase this, and when I write this, it will be clear. Okay. En equal to, I mean, I am going to deal with one particular subset. Okay? En f from that, such that there exists a x naught in 01, such that f of x minus f of x naught, okay, is less than or equal to n times, such that f of x minus f of x naught is less than or equal to n times x minus x naught for all x in 01. Okay, I call this as En. Yeah, we are trying to prove no where differentiable continuous functions form a second category. That means it cannot be written as countable union of no variance subset. For that, I am proving function differentiable. I mean, this is nowhere differentiable, not differentiable at any point. So function differentiable at least one point. You take that collection. That is first category. If I prove this, this is proved. Because if you have a continuous function, that's a complete metric space. So that is second category. C01 is second category. Okay. Suppose if I prove this is first category, this will be second category. Complement of first category in a second category is second category. Okay. That's why. So for that, I need to prove whatever I'm. Yeah. There are only one thing. These two are different statements. Same statement, equivalent statement. This is equivalent to, or this means this. That is okay. This is okay. That is f is continuous. Okay. 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 So I take En to be this. Yes, sure.
The lower one implies the first statement.
Lower one is implies the other statement. Correct.
Other way doesn't.
Other way doesn't work. Correct. Sorry. Yeah. Other way doesn't work. Correct. Okay. This implies that. It is enough to prove this, not that is. Okay. This implies this. Yeah. Okay. Correct. I mean, this is not implying this. This implies that. It's enough to prove this. This is okay. If you like it, this is the statement of the theorem. Nowhere differentiable continuous function is of second category. Okay. So enough to prove that D equal to all those f in 301, f is differentiable. Okay, this is good that you are very rigorous. F is differentiable at some x naught. Okay. To take all functions which are differentiable at some point. Okay, so that is D. Enough to prove D is of first category. Okay, to prove that is second category is enough to prove this. Now I defined En. En is set all those f such that this inequality is satisfied, which of course should remind you about derivative. Okay. If derivative exists, this divided by this divided by this is f prime of something in that f prime of something. Okay, and that will be bounded by something. If it is something, that's a some number. Otherwise, if except x naught, everywhere else, this is a continuous function. This divided by this is a continuous function, except at x equal to x naught. So continuous functions are bounded on a compact set on 0, 1. So only at x naught you need to worry about it. Okay. If it is differentiable, then that's a convergence sequence that will be bounded by some n. That has to be bounded. What I am saying is, if f is differentiable at x naught, okay, then there exists a m such that f of x minus f of x naught, okay, is less than or equal to, there exists a n is okay, n times mod x minus x naught. Okay. You can take this, I mean, you can take some interval x naught plus minus epsilon x plus epsilon. There exists an interval x naught minus epsilon, x naught plus epsilon, where this divided by that is bounded by some number. And the complement of this is continuous. This is a continuous function, no? F of x. Should I explain you all that? F of x minus f of x naught divided by x minus x naught. That's a continuous function. If you take out an interval around x naught, except x naught, but if you take an interval around, if you take an open interval around that, it is it's continuous on a compact set. These two, 0 to closed interval this, here to closed interval 1, it's a union of compact set. So there it is continuous, there it is bounded. Only here the derivative exists. I mean, there exists epsilon where the sequence is converging. So this should be thus divided by that, it exists. That limit exists. That's what derivative means. So it should be bounded. Okay. So it should be bounded by some n. So from these two statements, we get the following. For all x, in a neighborhood, it holds because it's differentiable. Everywhere else it's continuous, so it will be bounded. Okay. differentiable at x naught, then this is true for some n. Okay, exercise. I have given the proof. I have to orally told you the proof. Okay. So that statement implies that D is contained in union of E. Okay. This statement, En is defined like this. This statement, if F is differentiable, there exists a n. Okay. So this implies D is contained in this. When you take an interval out, then that is compact. Hmm. It's not. It doesn't mean, yeah. But I am taking out an interval. There exists an interval where it is bounded because it's convergent, no? Derivative exists means that divided by that is convergent, right? Derivative exists means something converges. You work it out, okay? It converges. That means there exists an epsilon neighborhood around that where it is bounded. Hmm? Exactly. Yeah. And the complement, it's compact, it's continuous. So, okay, it's not at x naught. It's an interval around. So D that from that, I mean, this is just a remark. So because of this, it follows that D is contained in union of n equal to n. So all we need to prove is each of these En is nowhere dense. Okay. So only enough to prove, only need to prove that statement that nowhere differentiable functions are second category, to prove that D is of first category. So we only need to prove each En for any fixed En. Okay. Each En is nowhere dense. That means each En is closed and interior of En is empty. Okay, that's what we mean by nowhere dense. What motivates to prove the theorem? I mean, people must have tried this for a long time and came up with this. Okay, there is no real motivation. If there is a very easy intuition or motivation, then they would have found it when they defined metric space, right? It must have taken a long time to prove this. There is, I mean, this motivation is because it reminds you derivative, right? Derivative is something like this. Then, I mean, to prove something, first of all, when there is no theorem, it is not clear that nowhere differentiable function exists. Once you have found something, then there is your intuition that it cannot be something. I mean, how many are there? It should be, the set should be very large. That is your intuition. That's your experience. Okay. So people try to prove that it's second category. People think that, I mean, I'm just imagining. I don't know the history. Okay. That is how usually it is like that. Okay. So it should be that it should be of second category. They want to prove. So you want to consider derivative and other things. It's natural to consider this kind of inequality. Okay. So only need to prove En is closed and interior and zero interior. Okay. That's what we need to prove. So these are the two propositions. I stated as two proposition. Proposition each En is closed. Then we will prove that it has empty interior. Okay. En is closed and it has empty interior. Proof. En is closed means you take Fn. En is closed means it is closed in C01. Okay. We are considering our universal space is C01 in C01. So we take Fn in En and Fn converges to F uniformly. Okay. That's what convergence in C01 means. Okay. In the infinity norm. Then we want to prove F is also in En. En is only a use, no, not Dn. Okay. We have to prove that F is also in En. Okay. Fn is in En means Fn in En, that just means there exists a Xn in 0, 1, okay, such that f of x minus fn x, fn xn, okay, is less than or equal to n times x minus xn for all x. Okay, that's what it means by definition. Okay, now we have to show that, we want to show that, if I mean, need to show, we need to prove f is in En. Okay, that is what we, our aim is to prove f is in En. Tell me, what are we trying to prove? What are we trying to prove? We are trying to prove it's closed. It's closed in what? So Fn converges to F in uniformly, then we have to prove F is in En. That's what we want to prove. Okay. Now, by definition, Fn's are in that Dn means this by definition. Now F is, we want to prove F is in En means we have to produce an element for F, a similar, an element satisfying that inequality. That's what you have to prove. Okay. So we have to prove that. So now this Xn is in 0, 1, which is compact. I mean, this is compact. 0, 1 is compact. Okay. So there exists a subsequence which converges, and then we have to work with the subsequence. So without loss of generality, we assume this sequence converges. Okay. We need to go to a subsequence, but without loss of generality, we take that sequence xn and that function fn. Okay. So without loss of generality, assume. I mean, we only have to produce an x naught. This is not going to contradict anywhere. Okay. I mean, if you want, we have to take a subsequence, work with the subsequence, get an x naught, and that x naught will work for that. That's, we only have to prove that. That's not going to affect the proof. Okay, and you should be careful why we are doing. We want to prove Fn converges to F and F is there. So for that we have to produce an x naught. That x naught we will get from the information of xn. Okay, so xn has a subsequence which converges because it's compact. So we take that x naught. Okay. Otherwise, we have to work with the, I mean, we assume that without loss of generality, xn converges to some x naught. Okay. Okay. Now our claim is x naught is the point we want. Okay. That's what we want to prove. The claim is, this is what we want to prove, or we need to prove enough to prove f of x minus f of x naught, 1 second, less than or equal to n times x minus x naught. Yeah. Xn is not Cauchy. Xn is Cauchy. Correct. Xn can, no. I'm not saying anything about Cauchy. It is compact, so it has a subsequence. Hmm. Yeah. Yeah. What is differentiable? No, no, we are not talking about differentiable. We are only proving En is closed. Okay. Differential functions are contained in that. Okay, we are proving a bigger set is no variance. Okay, that's all. We are proving some bigger set is no variance. If it is differentiable, it is going to contain one of these Ens. It may not be in En, in one of these Ens. Each En is no variance. That's what we are proving. Okay. So we need to prove this. Okay. But what we have is following from the original equation. We have this equation. Okay. So let's consider this f of x. Okay. We need to prove this. Okay. Let me write it. It's okay. F of x minus f of x naught is less than or equal to triangle inequality, of course. F of x minus fn x. Okay. Plus f of fn x minus fn x naught, okay, plus fn x naught minus f of x naught, of course. Okay. I have just written as 3 I have just triangle inequality. Okay. Okay. Now the first one is f of x minus f n x. This is less than or equal to n times x minus xn. Okay. No, sorry. This goes. Sorry. This goes to 0. Sorry. This goes to 0 as n goes to infinity. Similarly, f of x minus f n x minus f n x naught minus f of x naught. This goes to 0. This is, I'm using uniform convergence because for two different x and x naught, this goes to 0 as n goes to, I mean, I'm not even, I mean, this, both of them will go to 0 irrespective, but where I am using uniform convergence is, this will be less than, there can be a uniform, this will be less than epsilon, okay, epsilon by something, so let's say epsilon for some, okay, it's better to write it, because we are using, we get a uniform n for these two to be above that, for all, for some n greater than or equal to n naught, okay. After some n naught, this is less than epsilon by 3. Epsilon, I mean, you will get a some number, 5 epsilon or 6 epsilon, doesn't matter, okay. So this is less than epsilon, this is less than epsilon. So we have to consider the middle term, okay, which is fn x minus fn xn. Fn x minus fn x naught for now. This is less than or equal to fn x minus fn xn, okay, plus fn again fn xn minus f1 x naught, okay. That is less than or equal to fn x minus fn xn. This is less than x minus xn because fn satisfies that property, okay. This is less than n times mod of xn minus x naught, applying to xn, applying to x. Okay. Sorry, here applying to x naught, here applying to x. That is, this fn satisfies that inequality for all x. Okay. So using for any x, in particular for some x naught, this is true. Okay. Fn is satisfies that inequality, so it's true. That's all. That is true for all x. You take x equal to x naught. This is general x. Okay. Now this, yeah. Now this will go to where? No, this will go to n into x minus xn, x naught. Okay. And this will go to 0. Xn goes to x naught. Okay. Xn goes to x naught. Okay. So this goes to this, that goes to this. Other two are epsilon. I mean, if you want, you can take it. Other two are uniformly bounded by epsilon. Okay. Here we are using only the convergence of x naught. So the whole thing, so this implies f of x minus f of x naught is less than or equal to n times x minus x. This is the only thing which survives. You please, if there is a small thing which I want you to write. If you, I'm saying the first term is less than epsilon, second term is less than epsilon. Maybe you take this n, okay, this is n naught, okay. Maybe you take a bigger n naught so that this is less than epsilon by, okay, and this is less than, not, no, this is less than epsilon. This is near x minus x naught, whatever, okay. Then this is true. Then other epsilon will go to 0. I mean, not epsilon will, the epsilon is arbitrary, so it will go away. No, same capital N. We are fixing the capital N. There is no capital N. This only is varying. Capital N is fixing. We fix. Capital N comes with that En. That is in that bound n. This small n is the one which is, that is why I used the n naught, because there is a capital N there. I have used the n naught here. Usually we take this as capital N, but I called it N naught because capital N is there. Here there is nothing. The next one, proving the interior, there is some work has to be done. This is okay. This is not complicated. N tends to infinity. Okay, by taking N tends to infinity. Okay, if you want, this is less than 2 epsilon. Okay, now taking epsilon going to 0, we get this. Okay? If you want. Okay, take epsilon going to 0, so that goes. Here you can take n goes to infinity, then you take epsilon goes to infinity, epsilon go to 0. Okay, now the next one is interior of En is empty. Okay, interior of En empty is, you take any function here, any point here, a point is a function. Okay, you take an epsilon ball around it, that should intersect with the complement. That's what it means. Okay, by the interior, that does not exist interior. Okay, so for that we need another lemma. To prove this, we need another lemma. You know, piecewise linear functions, which are just lines like this. I will tell you, I will draw the picture how we are going to prove this. Okay, how interior of En is empty, we want to prove. That is we want a G in En complement. Okay, we want a G in En complement such that is for all epsilon greater than 0. We want a G in En complement such that norm of F minus G is less than epsilon, right? That's what we want. Okay, that's what we want. The ball around F with radius epsilon intersect with the complement. That's what we want to prove. So we want to get a G in En complement such that F minus G, the distance between them is less than epsilon. Okay, we want infinity now. Yeah. Arbitrary F, arbitrary specific F. For the time being, yeah, we fix. When we work with that, we fix it. But it's arbitrary. We are proving that for all, for epsilon greater than 0, oh, this is what you are asking. Okay. For F in En. For epsilon greater than 0, for F in En, we want a G such that this is less than epsilon. Okay. Given a F, given an epsilon, we have to find a G such that this happens. Okay. How this happens? So F need not be differentiable or something. So assume that F looks like this, some function. Its graph will look like that. Okay, assume this is just for intuition. Okay, so F plus epsilon is something like this. It is in this gap, anything in this gap. That is what F plus epsilon is. We want to get a function whose graph lies within this band. Okay, that's what we want to get. So first what we do is we take a linear function. We fix points like this, some points, few points like that, and we just connect it by lines. Okay, linear, which is continuous, of course, line. Now we have got a piece, I mean, not line, but it's linear means it's line. Piecewise linear means it's there are finitely many points which are joined by lines. Okay, so we take such function. Okay, that function which fall within this band and whose endpoints lie in this graph of that. Okay, you take F. This is what I'm saying. You take F like this, then you take points here. Okay, I mean this point will depend on the F and other thing. Given epsilon, there will be a delta, and we will use that. Okay, we will approximate by epsilon. Okay, like this. Okay, we will approximate by function like this, which is piecewise linear function, such that its distance between them is less than epsilon. We take some function. Now we have got some function, but we want a function which violates that condition, right? Violates this condition. That is, G is in En complement. So it has to violate that condition, whatever the definition of En. En means this is satisfied. We want this is greater than that. But what is this n for a linear function, for a line? Slope, right? It's a slope. So we will take, so if we have a function like this, okay, again within that epsilon, we will take very steep one. It is just the slope, but still the distance is less than epsilon, like this. These are again linear, but there are too many of them, which has a steep slope. Okay, that's all. That's what we are going to do. It's on the same thing. We are interpolated already there. Along that, we do something like this so that it will still be within the range of epsilon from that. That's all. You add an epsilon, there is a epsilon. Epsilon gives you a band. Okay, within that, any function will be at a distance of epsilon. Okay, so first we approximate by a linear function, piecewise linear function. Then we take another piecewise linear function using that, or we just take it and then add that function, add this kind of function. Okay, so sawtooth function or something, you add that so that the function will look like this. That function will be again within the epsilon band. We will make it rigorous. Okay, so that will approximate that, and that will have a slope always something greater than n, so that will not satisfy that inequality. Yeah. No candidate will x naught will we show that? Yeah. That you can do, but all points, this some you are approximating with something where the slope, where all the point is like this. What triangle? No, no, no. For all x naught, if you have a line, f of x minus f of y divided by x minus y is just the slope, which is constant for as far as between the except the endpoints. Okay. Okay. So this number will be greater than that. That's all. F of x minus f of x. Forget. We want to prove. I mean, we don't say that does not exist. We want to say that does not exist in x naught. So if this inequality is violated for all y, where you put y here, then there does not exist in x naught, right?
The slope of the triangle side. That slope.
Correct. But what is triangle here? Line. Okay. Why do you? There's no whatever. If you, as far as you look at the right object, it's fine. Okay. Function is, this is not, we are talking about differentiable function at some point. We are only, this is an abstract proof. We are not constructing an over differentiable function. We are only saying that no other differentiable functions are big. So we are showing that function differentiable at some point is very small. That's what we are showing.
If we take n2, like the slopes infinity, then it will be good.
If you select
The slope that we are increasing, if this we take to infinity, then it will be a node.
Why do you have to show it's convergent and all that? No?
Yeah.
It is a proof should, I mean, one should have got this proof idea from that only. Okay, this kind of thing. So once you have one function, then you should be able to do this for all function. I mean, that should be the intuition. Okay. Do you know Brownian motion? Have you heard Brownian motion? Physics. Brownian motion, when you construct mathematically, it's a measure. We talked about measure in probability course. Okay? Not defined very rigorously, but something. Brownian motion is a measure which has the support on nowhere differentiable function. Okay? Is measure of all differentiable function, that will be 0. Okay? Brownian motion is like it's a path of some Brownian particle. Brownian motion is a measure. It's common. Brownian motion is a stochastic process and all that, which as we talked about. But it's basically it comes from a measure. Measure is a probability measure we talked about. That is supported on nowhere differentiable function. Brownian motion is any path for a Brownian particle. So that path will be nowhere differentiable. Well, in reality, it will not be like that. Whatever Brownian motion is, there will be somewhere it's smooth, but this is an abstraction. Okay. So we want to, what do we want to prove? We want to give an AF. Okay, let me start from this. Okay, let me prove this another lemma. Let rho, let P, script P equal to all those F is 0, C 0, 1. Okay, F is piecewise linear. That is, piecewise linear means there exists x1 up to xn, x1 x1 greater than 0, x1 equal to x greater than x not equal to 0, up to xn equal to 1, okay, such that f restricted to xi plus 1, of course in the end point it should be same, okay, is straight line. Straight line is a function, you know what it is. If you are given just 2 points, okay, I mean this is just a straight line. F between here is a straight line joining these two xi, f of xi. This is a element, okay, and xi plus 1, f of xi plus 1. Once you know 2 points, then there is only one straight line joining that. So that defines a function, right? Okay. If you do, what is the formula? Y2 minus y1 by y1 minus, I mean something. Y is equal to xi, you know the formula, okay? So straight line formula, from that you know y equal to that is a function, okay? If you are given 2 points, then there is a unique straight line joining them. There is a unique function defined by that, okay? Between f restricted to that interval xi plus 1 is that straight line, and f of xi, I mean there is a straight line before this, that end point and this, I mean, you know, but by definition that is clear, okay? Is a straight line joining these two, that's all. Okay? The previous straight line should join f of xi minus 1 and f of xi. Exactly. We are just taking some n points and it is just the piecewise. This is clear, no? Piecewise linear. Piecewise it's line. Linear means it's not the linear in vector space theory. It's a straight line. That's what it means. Okay, okay, this is clear. Okay. Then rho is dense in C01. Okay. Not rho, P is dense. Piecewise linear functions. Piecewise linear functions are dense in C01. Okay. So F is uniformly continuous on C01, on 01. So we want to prove this is dense. Okay. So we have to prove F is in C01. Okay. Then we have to get a piecewise linear functional, some P, which is at a distance less than epsilon. Okay. We have to produce a P. Okay. Given a F, we have to produce a P such that the distance between them, the infinity distance between them is less than epsilon. That's what we have to prove. Okay. So I have taken a F. F is continuous means it's uniformly continuous because it's 0, 1, compact interval. Okay. So given epsilon greater than 0, so we have to get a P, piecewise linear. Given epsilon, we have to get a P. Okay, now because it's uniformly continuous, given epsilon, there exists a delta greater than 0, such that f of x minus f of y is less than epsilon if x minus y is less than delta. Okay. Now choose x naught 0 equal to x naught less than x1 is then x2 up to xn equal to 1. Okay. Such that the distance between them is less than delta. Such that mod of xi plus 1 minus xi is less than delta. I believe this will work. Just join the lines. Okay. Now let P is the piecewise linear function such that joining xi f of xi and xi plus 1 f of xi plus 1. Okay. Those 2 points, you just join it by a straight line. So that is what is this P is, small p is. You got a piecewise linear function. So we want to see whether it works. Okay. I think it should work. Okay. Now we want to prove the distance between them. Distance between P and F is supremum of this. Okay. So this is uniformly bounded by some epsilon. That is enough for us. The epsilon is given. Maybe 1 epsilon, 2 epsilon, 3 epsilon we will get. Okay. Doesn't matter. So this is something times epsilon could be there. So f of x minus p of x. So as we know, what do you have? F of x minus f of. So for x in here, x in 0, 1. Okay. So this implies x is going to be in some xi plus 1. Okay. For some I. Okay. X is 0, 1, that is going to be in one of those intervals. Okay. For the proving this inequality, I take that I. Okay. Here there is no I. Okay. So this f of x minus f of xi. Now f of xi, maybe I plus 1, shall I take? Maybe I plus 1. Okay. Now f of I plus 1 minus, this is p of xi, right? P of x. Okay. Partition is constructed less than delta. That distance is less than delta. That's all. Yeah, but where I have written it there. Yeah. Oh, didn't I say the distance is less than delta? Where is it written? It's written. Yeah. Xi minus xi plus 1 is. Maybe I thought I forgot. That's why I choose the delta. The reason for choosing delta is that distance is less than delta. Okay. Now x is in this. So xi, this distance between xi and xi plus 1 is less than delta. So this should be less than epsilon. Okay, now we want to show this is less than epsilon. Okay. So f of, okay, first f of x minus f of xi plus 1 is less than epsilon. We have got it. Now this f of xi plus 1 is nothing but p of xi plus 1, because that is how p of x is defined. It is in the end point, it is equal. So this is just p of xi plus 1 minus p of x. Okay. Now if you see, if you have a straight line joining 2 points, okay, there are many versions of equation of a straight line. If you have this point, you call it as xy, x1, xi. This point is xi, f of xi. Okay. This point is xi plus 1, f of xi plus 1. Okay. Then the equation of the straight line is actually given by t times this point. You call it as a. You call it as b. Okay. T times a plus 1 minus t times b. These are all the points when t varies from 0 to 1. This is okay for you, or some more explanation is needed? This is okay for you. That is how all points are there. So if you take a point, any 2 points, some arbitrary point xi, and r, so this is kind of distance on the line. This minus this, if you take this, any point is going to, there is going to be a corresponding, this is t equal to 1. Xi plus 1 correspond to t equal to 1. This is for some t. So this is just p of t, p of 1 minus p of t. That will be greater than p of 1 minus p of 0, because it is just the distance on the straight line between any two. Is it clear to you, or one should go through this? Okay. This line f of xi plus 1 is defined to be p of xi plus 1. That is how p is defined. That is how p is defined. Okay. That is just the straight line joining that. So I am just saying that this is less than or equal to, all I am saying is this, p of xi. All I am saying is this, that is less than this, because this is the distance on the straight, this is the distance between on the straight line between x and xi plus 1. This is the distance between xi plus 1 and xi. This distance is greater. Okay. You
This is just like saying this.
exactly, this is, if you look at this parameterization, it is clear. This is just some, this corresponds to 1, this corresponds to some t, this corresponds to 0. So this is just the distance on the straight line. Okay. You think about it. I have written it as exercise. Okay, this is just a 10th standard exercise, maybe 12th standard. Sorry, coordinate geometry, 12th standard exercise. Okay, this is just the. Okay, I think it's clear. Just 12th standard. I mean, if you must have prepared for, maybe not in 12th standard, but JEE and all, you must have prepared. And this is a very easy exercise when you are prepared for JEE. Okay. So that is less than that. Now we know that p of xi, this is again, now this is equal to f of xi plus 1 minus f of xi. Okay, that is less than epsilon. So this implies f minus p, this is true for all x, is less than 2 epsilon. That's what we wanted. Maybe you take, wherever I said, you take instead of epsilon, you take 2 epsilon. Epsilon by 2 there, or you take this epsilon, replace epsilon by 2, or there you take 2 epsilon, doesn't matter. Okay. So we have proved it. So proof of the theorem, proof of the rest of the proof of the theorem. This concludes the lemma. Yes. So it is less than 2 epsilon. Maybe you take epsilon to be epsilon by 2, that will work. Okay, whatever. Okay. Now given a f, we have got a p at a distance less than epsilon in C01. C01, uniform distance less than epsilon, which approximates this. Now, as I said, we take this high slope thing. Okay. Now let h of, I mean, we are still having a f. Okay. So let f is in En. Okay. First choose p in rho such that f minus p is less than epsilon. Okay. That we have done already. Such a thing exists. It is dense. Okay. Now let, so we are given an epsilon. All we have to use is just, so, G is not P. We are going to have one more thing. Okay, I need this, sorry, I need this, I need that delta xi is another thing.
Taking here, this.
No, it is not any P, we take this P, okay? I mean, that's what P as in the earlier lemma. Let f is like that, and let xi 0 equal to x naught less than x1 less than x2 up to xn equal to 1, and epsilon and delta, let f is this epsilon greater than 0. and delta as and xi minus xi plus 1 minus xi is less than delta, and p as in the lemma. Okay. Okay. I mean, exactly like this lemma. P is just a linear function connecting f of xi and f of xi plus 1 between xi and xi plus 1. Okay. Those 2 points as in the lemma. Okay. Then we know that distance between f and p is less than epsilon. Okay. Or epsilon by 2, because we may bring in something else. So now define some h of x h of x I equal to 0 for all I, and h of xi plus xi plus 1 by 2, the midpoint, okay, equal to wait, I have to choose epsilon, I have to choose, if you want to say, given epsilon you get a delta, no, that is how we got p. Given epsilon, so that the distance between f of xi plus 1 f of xi is less than epsilon. These things fixed in the earlier lemma. Okay, that delta, that epsilon, that p as before. I need not have stated as a separate lemma, just the proof is very long, so I separated as a separate lemma. You assume that that is also inside the proof, then there is no problem. Okay. Okay. This is equal to m, where I will tell you what is m. This is equal to what? This is equal to epsilon. No, this cannot be this. This is epsilon. Sorry, this is epsilon. Sorry, wait. This is epsilon. Wait, this is epsilon. Wait, let me think. This is epsilon. We need only the slope to be very high. Okay. No, wait. No, we still have to choose the delta. Wait. No. We need to have further smaller delta. Sorry, I will erase this. I will start from, we don't need this. That is okay. We don't need this. We need a fresh xi plus 1. I am going to use the lemma. I haven't used the lemma. Yeah. First we get a p, then we get that function. Okay. Using that we get a function. Okay. Proof of the theorem. Forget about that. I get a new delta given epsilon. Okay. So now f is, let's start with f is in 0, 1. Okay. And p in p such that this is okay. F minus p is less than epsilon. Okay. Okay. Now, yeah, now we want the slope to be very high. So let m be greater than n maximum of n and something more, and all those mi, I equal to 1 to n, I equal to 1, all those whatever mi, where mi is the points of not the partition. The p has some points, no, n points of those piecewise straight lines. What do you call points of singular or non-differentiable? What is it called? Pointed. I mean, what is the word for it? You have this look like these points. Point of not discontinuity. Point of where it's not differentiable. These are points where it is not differentiable. N points of the piecewise linear thing. Okay. Im where sorry, where mi's are slopes of the individual straight lines. slopes of individual straight lines. Straight lines of P. P consists of several straight lines. Each straight line has a slope. Okay, that is Mi. Huh? Yeah. Each has a slope. We start with F in En. Pardon, this is En. Sorry, F in En. Okay, for that F we choose a P. Okay, Mi is the slopes of all the individual straight lines of P. Okay, and N is of course fixed. We take a M which is greater than this N, Mi, all of those things, and we are given a epsilon also. Okay, like this epsilon greater than this. We are given epsilon, F, P, and all these MIs, and we choose a M which is greater than all these things. Okay, I have to go there. Okay. Now we want top xi. That should be okay. Let's define and choose M later. Okay. So define.
Take the distance divided by
No,
epsilon.
wait. That's what I'm going to do. Now choose. I will choose the delta here. Okay. Now choose 0. The delta will be chosen. Okay. X0 less than X1. This is a different one, not the earlier one. This is a new one. Okay. Up to Xn equal to 1. Okay. Such that Xi plus 1 minus Xi is less than delta, where we are going to choose the delta. This has nothing to do with epsilon. Okay. It will have something to do with epsilon, but not through continuity or uniform continuity. Okay. This is less than delta. Okay. Now, such that that difference will be epsilon. So epsilon by, so we want M to be greater than epsilon by delta. Epsilon by delta. So this is delta should be less than this, right? But epsilon by delta. M to be less than epsilon by delta. Why it less than that? We want M to be, we have a M and we have epsilon by delta is greater than M, right? So delta to be less than epsilon by M. Good. Okay. Now we have chosen delta. Okay. I started with F. I choose a P which is closer to epsilon by the earlier lemma, which is through earlier lemma. Then I have taken, I will not take the Friday's class, so I am taking more time. Okay, I will stop with this. Okay, so because you have exam on Saturday, so I am not having Friday's class, so I will take 5 more minutes or something. Okay, yeah. now you are allowing me to take. Okay, so now I have chosen M, which is greater than this N, and all these MIs are the slopes of the individual straight lines which constitute the P. Okay, now this is greater than this. Now you take a delta which is less than epsilon by M. Okay, that is epsilon by delta is greater than, sorry, M is greater than epsilon by delta. Okay, and it is of course greater than 0. Okay, greater than 0 also. Okay, okay. Now define h of x, h of xi. Now we have taken xi to be like this, h of xi equal to 0. Okay, and h of xi plus 1 by 2, okay, equal to epsilon. Okay, then join. Actually, I am only taking something like this. You can actually, if you want, you can go like this. Then I have to write more, but this is okay. Whatever You can take any one of them. Okay? That will also be something. So join by straight lines. Okay. Okay. Fine. Join xi f of xi f of xi plus 1 xi plus, this is just the midpoint of this. You have xi plus 1, you have the midpoint. Okay, you join here it is 0, here it is 0, here it is 0, here it is 0, everywhere it is 0. The midpoint it is epsilon. Okay, so it goes like this, it starts here like this. Okay, so only this way. If you want, you can bring it like this and do this. That is another, I mean, but this is okay. I have to make another definition then. Odd, even, something, so it's okay. Okay. This is like this. Then slope of this, then slopes, I mean, it's not slopes, slopes of all straight line. Okay. Slopes of h is greater than m. Slope of h is, this is m, actually m by 2 or m. Yeah. Maybe I should take epsilon by 2, no, equal to epsilon by delta by 2 you will get. So you will get 2m. Oh, it's okay, it's much bigger. Okay, no, it doesn't matter. So epsilon greater than m is fine. Right? What is the slope of this straight line? The distance slope is yi plus 1 of any straight line is yi plus 1 minus yi divided by xi plus 1 minus xi. Exactly. Here it's the midpoint. Okay. So the midpoint, it is epsilon 0. Then the midpoint, which is xi, which will be xi minus xi plus 2, but by divided by 2. Okay, you get a 2 here, whatever. And that 2, you can calculate it. Slope of the straight line, you can calculate it. That is greater than m. If it is not exactly m, somewhere you add 2 or 1 or something. Okay. Okay. So you get this is greater than m. That's what we want. Some constant time m is also fine. You can adjust. How is m greater than here? Here. Here. M is greater than epsilon by delta. Yep. So where is the mistake? M is, huh? Epsilon by delta. Delta we take it, is it m by, no, not m by epsilon. Now what do we want? Okay, let's calculate it. Then I have to calculate the slope. So what is the slope? So slope of this is h of xi plus xi plus 1 by 2. Okay, h of xi. Okay, divided by xi plus 1 by 2 minus xi is xi plus 1 minus xi by 2, right? This is epsilon, this is delta. So this whole thing is epsilon by delta. You want epsilon by delta to be greater than m. That's what you want, right? So this should be this way. Epsilon by delta is greater than m. So if say epsilon m is, yeah, this is okay. This is okay. That's what you want. Okay. Okay. Now you calculate it. Then the this is greater than m. I just calculated here. Erased it. I just slope of the, if see, define h of xi equal to 0. You have something x1, x0, x1 up to xn. Okay. All these points h is 0. The midpoint is epsilon. Join by straight line. That straight line will have slope h of xi plus 1, which is epsilon, minus this is 0, which is epsilon, divided by the length of that. The length of that is delta by 2. Okay. Delta by 2, whatever. So this is greater than m. 2m or whatever, or even m by 2 is also okay. Then you can change it, change the delta, whatever. Okay. Please take care of it. Okay. That is less than this. Okay. Now we have got this. Hs slope greater than m. Okay. Now define, now f minus, now take g equal to p plus h. Okay. This is sum of two straight line, which will not be a straight line, but that will have slope. Now mod of p plus h, I mean g has this has slope, this has, I mean this has slopes mi's everywhere. This has slope greater than m is greater than all those mi's. It can at the most become minus mi. Okay. Sorry, I'm sorry. We need one more thing. Where is m? Where did I define m? Can you tell me where is it? This should be n plus mi. I'm sorry, please change it. It should be n plus mi. Then only that will be greater than n we want. I'm sorry. Not mi, n plus mi. Okay. If I prepare the notes and reproduce all these things, then I will not be thinking about these things. Okay. N plus, yeah. Huh? Yeah. You don't need to include. Initially, I included, but it's not needed. Yeah. That's for I. I. N plus mi. You can include n also if you want. That will be max. Yeah. You can take n also if you wish. That will be the same. Yeah. No. It is just, I initially wrote mi, so that's why that was there. N is not needed now. Okay, n plus mod mi. So, no, n plus mi is also fine, no? Because we are taking n plus mi, so it doesn't matter. We can take any big number we want. We can take 1,000, I mean trillion times m also will work. It doesn't matter. So g, now this g satisfies the following. Now g of x minus g of y, okay, is less than or is greater than or equal to m times x minus y. Okay, for all xy. Okay, this implies, I mean, sorry, n. We wanted n, no, not n. G is the sum of these two things. H has m. The m is for h. P has all the mi's. So when you sum these two things, it will satisfy this. Okay. If you want to use, you can write it by triangle inequality if you want. Okay. So it satisfies this. Okay. P has slope mi's. H has slope greater than m. So the sum will satisfy this. Okay. Okay. So this implies G is not in En. And F minus G is less than 2 epsilon. We are done. So we can take questions now. Please come. Talk.
I should think, like, say for instance, we have this function. So this is our f,
Yeah.
and then this is our linear. So
This
this
is the
will
first
be
P we are taking.
Yes, sir.
Up,
So this
it's
is
approximating. Yeah.
yes. So when we do this, and then now, which is say for instance, this is xi.
That is not xi anymore. Now we are taking a new xi's. Maybe I should have used yi, but yi will confuse with the range one, no? Y-axis one. So that is why this is a new xi. I am sorry. Don't confuse this xi with the earlier xi. Yeah, that's why there is a separate proposition where the xi's are taken and finished. I initially said that, but then erased everything. But maybe it's not erased in the memory.
For example, how do you know that p plus h will necessarily be in the
No,
epsilon?
P we have chosen. P is made up of mi's. Those mi's are taken into account here. When you take m is greater than this, m has slope greater than n plus mi. right? So m has slope greater than this. Okay, so P has slope mi, H has slope greater than m. So the sum will have slope, sum will satisfy this.
But then we also need to show that P plus H, this function G that we're defining, that
Yeah.
will always lie in that epsilon band around up.
Exactly. This is, oh, okay, that's what you want. Okay, F minus G is equal to that H. That is less than epsilon. Okay, is that what you are asking? This has maximum values epsilon. H has maximum values epsilon. Okay, norm of H infinity is less than epsilon, equal to epsilon, in fact.
F minus G always goes to F. Like, is that how we're defining it?
No, it is 2 epsilon, sorry. F minus G, F minus G, which is P plus what? H, okay, which is less than or equal to F minus P plus P minus H. Just H, sorry, just H. Just H. This is epsilon, this is epsilon, 2 epsilon. This is fine. Sorry, I forgot to say. That is how we chose epsilon. H takes small values but steep slope. That is mod H is equal to epsilon. Yeah. Not mod H, norm H is equal. Eh? This is less than epsilon, no. So that's why 2 epsilon. This plus this. Correct. These are dense in C01. No, there has to be dense because I mean, see, we have then the complement will be second. Complement will also be some sort of second category. That will be dense. Because if it is not dense, okay, we have a complement which is already dense. You no, he's saying that why is it dense? Okay, that is anyway intersection. See, all these EMs are nowhere dense, close to nowhere dense. Okay, their complement is open and dense. Open and dense. Intersection of those complements are contained in nowhere differentiable function. Baer's theorem says that intersection of the complement is dense. So it is dense. Okay. Yeah, we are using Baer's theorem also. Generally. No, that is what the idea is. No, if it is second category, it cannot be written as nowhere dense open subset. Nowhere dense closed subset. Okay. So it's no, so not second category. It's the complement is also first category. We have the complement is first category. So that is contained in some nowhere dense union of nowhere dense thing. Second category, then that can be any closed subset. No, I mean second category is something to do any complete metric space is second category. You can have any complete metric space. Of course, false. You can take any complete metric space inside a complete metric space. That is second category. But what are you considering as nowhere dense subset? That is nowhere dense inside that.